Hey guys, welcome to part one of Force and Newton Laws of Motion notes. We're going to take this in two different parts. I just figured I'd split this up because it's a pretty long set of notes. Rather than give it to you all in one big long video, I'm going to split it up into kind of part one and part two. So in part one, we're going to talk about Newton's first law of motion, and then kind of some friction stuff. And then we'll get into action, reaction, and free body diagrams and stuff in part two. So, force. What is force? Well, force is any kind of push or pull acting on an object. It gives energy to it. It causes some kind of change in motion. It could be giving an initial push. It could be speeding it up. It could be changing its direction or slowing it down or stopping it. But all of those are required in order to force is required in order for all of those things to happen. So, we have seen force in action with our different kinds of motion that we've studied so far this year. It's just that we haven't identified that source of how the ball starts rolling, how your projectile gets launched, how we change the direction on a track or something like that. And force is that thing. So not all of these, and note here, all of these are forms of an acceleration. So again, a changing of velocity is what is caused by a force. Could be, again, a slowing down, a speeding up, a starting, a stopping, or a changing direction. But all those are a change in velocity, which means they're all a form of acceleration. All right. Force may sometimes change an object's shape, and just like with velocity, they are represented with vectors. So it is a vector quantity. It has both direction and magnitude. And we will look at some vector diagrams, which we call free body diagrams for forces, just looking at how all the different forces acting on an object interact with each other to find the net force. But that's going to be in day two. So we measure them in newtons, capital N, newtons, which is represented by kilograms times meters per second squared, meaning here my mass times the acceleration is what newtons is, which really what a force is. It's something we'll talk about with Newton's second law. Force is mass times acceleration, FMA. Here we represent mass in standard units in kilograms, acceleration in meters per second squared. So newtons are just that standard unit for those two combined. We can use a spring scale, which I should have had one before I came up here to do my notes, to measure them, kind of looking at the resistance that it takes in order to apply the different force, but that's something we can use to measure them. All the forces acting on an object together are known as the net force, and we'll look at the net force of different objects when we do free body diagrams. Any kind of balanced forces are equal to each other, so the gravity pulling down on you and the gravity pushing up on you are equal to each other, which is why we're not in motion. Any unbalanced force, here we go, yeah, no movement or change in movement occurs. The net force is zero. Here, this is kind of a preview of what free body diagrams look like. We have forces acting in the opposite and equal directions. If we have unbalanced force, that means we're going to have some change in movement. The net force is going to be bigger than zero. And here, this is what it looks like for it to be unbalanced. And when I have an unbalanced force, that's going to cause an acceleration. No matter which direction or how it's causing it, some kind of acceleration is going to happen. Again, whether that's speeding up, slowing down, stopping, starting, or changing directions. There's a whole lot of different number of forces out there, and kind of where the force comes from varies greatly. Gravity is the most common one. It's the one we've seen the most. It's a force that pulls down on an object depending on the size and the distance. We know gravity is acceleration. We know here on Earth that acceleration is 9.8 meters per second squared. Weight. So we talk about the weight of an object is actually the force of gravity on the mass. So a lot of times it gets kind of confusing because we talk about like the weight of something if you measure it outside of the US when we're not in standard units. We're talking about the kilograms, like how many kilos you weigh. But really it's talking about the mass that you are based on Earth's acceleration. When we're talking about weight, it really does depend on the gravity that you're experiencing. We don't have the same weight here as we would on the moon or on Mars or on Jupiter or anything else like that. It does not, or it is affected by the gravity, where mass does not change with gravity. So this is kind of getting into it a little bit here. This is kind of what we do for our force notation, which we'll get into again when we do free body diagrams. If we do F with some subscript here, so not like an exponent, but a subscript, that's just telling us the force the force of weight, so the weight force, is equal to your mass times the acceleration due to gravity. So if you wanted to figure out what your weight was, you would do in newtons, you would do your mass in kilograms times the acceleration due to gravity. Okay, so that's kind of just the basics of force, getting into Newton's 3 laws of motion. Most people have studied before. Maybe you guys did in middle school, back with, I think you guys are still Mr. Gardner science people for everyone in this class. I think so. I think you're the last group that had Mr. Gardner all the way through. I think you guys do some laws of motion stuff, Newton's 3 laws. And most people know what they say, or, maybe they don't know what they say. But if they do know what they say, they just don't know what they mean, really. So we're going to look at today and tomorrow, really this section before the final, is just looking at Newton's laws of motion. What do they mean? How do they interact with each other? So here are the first laws, just going through them real quick. Newton's 3 laws of motion. The first law says an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. Newton's second law says that force equals mass times acceleration. And Newton's third law says that for every action, there is an equal and opposite reaction. So getting into his first law first, which is the law of inertia. That's what that kind of term comes from, where an object at rest will stay at rest, and an object in motion will stay in motion unless that unbalanced force acts on it. That's what inertia is. Inertia is the tendency for an object to stay in its current state. So the more inertia an object has, the harder it's going to be to either change its direction, speed it up, or slow it down. Any kind of change in direction, a change in velocity, any kind of acceleration is harder to do if the object has a really, really big inertia versus a small inertia. So I got a little video here, and I turned the video into a GIF for us so we can kind of see. Again, this is a beautiful example here. So cool. So cool. Of inertia. So again, the leaves are at rest, and they have a tendency to stay at rest until acted upon by an outside force. So you can see that instant that the jumper, I don't know if it's a guy or a girl, it doesn't really matter. Looks like a ponytail, it's probably a lady. Hits that net and it pulls it down. Those leaves, that kind of instant that the bottom drops out on it, they still have that tendency to stay at rest, to stay in that same position until they're acted on by the outside force. Because right now, as they're sitting there on the net, they're at rest. The forces are balanced because the force that the net is pushing up on it against and the gravity that's pulling down on it with is equal, so they're just sitting there. But as soon as that net falls underneath and they don't have that upward force anymore, the only force acting on it is gravity, in which case then they start getting pulled down. But you can see that kind of initial delay of them wanting to stay at rest until they start getting acted on by gravity, which is kind of cool. So just kind of saying the same thing. Inertia is the tendency of an object to stay in its current velocity, whether it's in motion or motionless. These pumpkins are not going to move unless you're acting on by an unbalanced force. They're not going to go anywhere. Kind of the same thing for any kind of object in motion. Once it's airborne, an object is not going to kind of change unless there's an unbalanced force acting on it, which in our case, we actually do have objects acting on it, which is why they don't just stay in perfect motion. We have gravity acting on it and air fluid friction, air resistance acting on it. Because if that wasn't the case, they would just never stop. So if it's not going to be for those forces, the golf ball would sit on the tee forever. And once it's in motion, it's not going to stop being in motion unless, again, something acts on it, in which case, gravity and air resistance. So why do we observe things if there's no outside unbalanced forces acting on them, slowing down or becoming motionless without some outside force? Well, really, it's an outside force that usually we just can't see. Most outside forces, like most forces acting on objects, most commonly are what we call invisible forces. We don't actually see them. Gravity being the most common one, but we usually see that. But if we actually looked at like the path that we did, if we go back to those projectile motions, those launchers that you guys made, If we looked at the perfect ideal stuff, like we did in class at the beginning of chapter 2, when we looked at those different equations for figuring out the final distance away based on the initial velocity and the initial angle that we're looking at, they wouldn't match perfectly because in the real world we have air resistance and air movement that interacts with our objects as well, which friction is the most common invisible force that we don't usually think about. So on Earth, unlike objects in space, they're under the influence of friction. So we're going to talk a little bit about friction here. It's one of those unbalanced forces that acts on an object, usually to stop it from moving, not necessarily to give it any kind of initial motion or initial push or pull. It's usually forces acting in opposite of any kind of applied push or pull. And there's 4 main types of friction. We've got sliding friction, which I'll go through a little bit more. Example of that would be ice skating. Rolling friction would be like a bowling pin or bowling ball rolling along. We've got fluid friction, which could be air resistance or liquid friction, so like kind of going through water resistance. And the last one is static friction, which is an initial friction when moving an object. So I've got some different GIFs here of examples of sliding friction. We can see here the soccer player has a high coefficient of sliding friction. He tries doing that little knee slide, and there's just way too much friction, and he just plants it and then face plants. It's just awesome. While the cat down here, which, cat videos, that's cool. Really, really low coefficient of sliding friction, which in this case, obviously, he's kind of running around on ice and chasing after something, it looks like. But because there's a very, 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 very little friction there, he slides around and doesn't have a whole lot of grip on his paws and can't go anywhere. So sliding friction, again, is anytime you have 2 objects, literally like it says, sliding past each other. That's the most common when people think of friction. The most common type of friction, kind of what pops into their brain. That's just, again, that sliding friction. The kind of 2 surfaces interacting with each other, sliding past each other. That's sliding friction, as you would expect. Rolling friction, just like it sounds, is any kind of object that is rolling. It could be a ball. It could be a rolling pin. Kind of anything that would roll, and it's kind of got a circular shape. This one is very, very closely related to static friction because it's a little harder to understand why something that's rolling would have any kind of friction, because it's not really sliding past and kind of grinding at all. But what's actually happening here is the point that the ball or the object, the rolling pin, the cylinder, whatever it is that's rolling, on that point where it interacts with the ground, the tabletop, whatever it is, there's actually a little bit of attraction between those different molecules and those different atoms to want to stay together. And that is very small coefficient compared to like sliding friction or air resistance, depending on the kind of rolling that's happening. But there is still a little bit of that attraction for those atoms to kind of want to stay together, especially if they have any kind of opposite charges, to want to stay kind of in contact with each other. So there's a little bit of resistance as the object meets that point on the ground, and as it starts to try and pull away, there's a little bit of resistance there that want to stop it from rolling. Fluid friction, I would say, is probably the second easiest to kind of picture, because all of us have probably felt this before, whether you're driving down the road and you put your arm out the window and you kind of do this little thing here, right? You guys never done that before, where you let the kind of the air flow past your hand and you kind of let it dance a little bit in the wind. Or even if you just drive with the windows open, you can feel that air blowing against you. You've got that resistance that's stopping it from trying to move forward. So here we have a skydiving cat, which is totally real, I'm sure, that's experiencing that air resistance, that air friction. Again, it's like any kind of fluid, which gases and liquids are both fluids, meaning they free flowly into the objects or the containers that they're in. That's fluid friction. And again, here we've probably all done this before. This is kind of how a fish works. We're going to talk about that in a little bit here on how a fish propels itself forward. It's just, again, as you try and move through that liquid, you kind of feel that resistance that makes it more difficult to walk than just any other thing. Like if you guys were, waist deep in a lake or in a swimming pool or anything, trying to walk there is much more difficult than it is for walking on ground, because water has a much higher fluid friction than air does because of the density of it. And the last one is static friction. And this one's the hardest to see because you don't see it. It's just talking about kind of that initial getting in motion, that little bit of resistance. And again, it talks about here static friction because there is that attraction between the different atoms and molecules that are in contact with each other between the two different objects that kind of just don't really want to get started. They kind of want to stay where they are until you really lift up on it or start moving it forward. So it's a little harder to see, but here, the one that always comes to mind just kind of when I think of traction and kind of initial starting is starting blocks and track. You guys know I've coached that for a while, so that's just what comes to mind. Here, just someone getting into the starting blocks, and here his hands definitely have a much higher coefficient of static friction than his feet do because he kind of false starts and then does a handstand and looks like an idiot. So that's always fun to laugh about. Okay, moving along then. The last couple of things here. Sliding a book across the table, watch it slide in to a rest. Obviously, that's because of sliding friction. It comes to rest because of the presence of a force, being friction that's acting on the book. If there wasn't any of that friction, it would continue sliding and on and forever. Just that here it stops because it's either going to fall off the book, the tabletop, or whatever the case may be. Another thing here, and this is just my PSA, and this we're actually going to stop today. Newton's first law and you. Don't let this be you. Please wear seatbelts. Please drive safely. I know as teenagers we're not necessarily the most experienced drivers, and sometimes we feel a little invincible, but trust me, you do not want to make this you. This is why seatbelts are so important, because it increases the time in which the force acts upon you, which we'll talk about second semester with impulse and kind of collisions, how those interact with each other. The longer you can spread out the time that force acts on you, you can kind of distribute that force more evenly. But here, because of inertia, when your car hits the wall, however fast your car was going, your body, because it's traveling in that same that same speed, it's going to want to continue in that same motion until an outside force acts on it. And let's make sure that outside force is the seatbelt that slows you down with the car instead of throws you out of the car and then you're thrown at 80 kilometers per hour out the car because your car was traveling 80 kilometers per hour. Don't let that be you. Wear seatbelts. Be smart. Drive safe. And as always, if you guys have questions, concerns, thoughts, ideas, hopes, or dreams, let me know. I will follow with part 2 tomorrow. But that's all I got for you today. So have a fantastic day. See you guys soon.